Smoke spiraled from the seaside bluffs at Hope Ranch, and suddenly social media was ablaze. Eyewitnesses and local news crews buzzed that Santa Barbara had sprouted a new volcano on its shores. Could it really be an eruption? Geologists were swift to point out that no, it is not a volcano at all. In fact, for the record, there are no volcanoes in Santa Barbara County. What onlookers saw was a bluffside blaze driven by chemistry and geology, nothing magmatic. The scene unfolded on Thursday, April 23, 2026, when Santa Barbara County firefighters responded to reports of smoke at Hope Ranch. Plumes of white vapor billowed from the beach cliffs and were visible even from UC Santa Barbara's campus, a few miles away. About 3 miles, or roughly 5 kilometers away. Locals who first spotted it might have feared lava or steam, but Battalion Chief Michael Gray took it in stride. He said he had always just accepted it as the Hope Ranch volcano, emphasizing that fire crews treated it as a routine matter. Within hours the flames were doused, and firefighters were simply monitoring the smolder, not organizing an evacuation or emergency response. This phenomenon, while newsworthy each time, actually has decades of history. Newspaper archives show that the cliffs have smoked repeatedly in recent years. Spark-producing thermal events were recorded in 2017, 2019, 2020, and even July 2021. Each event generated momentary concern, and often brief brushfires on the bluff before settling back into quiet. The so-called Hope Ranch volcano name is something of a running local joke. As one long-timer put it, flames here pop up every couple of years, same thing. Even earlier, reports date to the 1800s in nearby Ventura County, where stagecoach travellers once wrote of a steaming mountain at Rincon Point. Clearly, plumes of smoke on Southern California's coast are not unprecedented. They are just rare enough to stir up modern social media. So, if this is not magma, what is burning? The answer lies in the geology of the bluffs and their chemistry. Santa Barbara's coast here consists of layers of sedimentary rock lifted by tectonic forces over millions of years. Geologists describe the area as part of the transverse ranges, a block of crust squeezed by Pacific and North American plate movements. These same forces thrust ancient seabed layers skyward through the Santa Ynez Fault system. But critically, none of this involves any current volcanism. As one university professor notes, it has been about 30 million years since Santa Barbara saw any volcano action. In other words, the rocks here are old and sedimentary, sandstones, shales, and similar materials, not part of a living magma plumbing system. These sediments are also rich in organic material. Off the Santa Barbara shore lies oil and gas that formed in the Miocene epoch, roughly 16 to 5 million years ago. Over geologic time, plankton and plants buried in seafloor mud turned into petroleum and bitumen within the shales. In fact, studies of the channel note that these hydrocarbon deposits sit unusually shallow, often only about 1 kilometre or roughly 0.6 miles below the surface, due to thin sediment cover here. The result is that oil and tar seeps have long been part of the landscape. The native Chumash used those natural asphalt seeps to waterproof their canoes, and even early oil wells tapped the Monterey Formation offshore. In short, the Hope Ranch cliffs contain both fuel, ancient hydrocarbons, and oxidizer air and moisture when exposed, plus a chemical trigger hidden in the rock. Enter iron sulfide. Common in those shales are veins of pyrite, often called fool's gold, and similar sulfide minerals. When such minerals meet oxygen, they can heat up dramatically. Geochemists have long explained that spontaneous combustion is initiated by the oxidation of highly reactive iron sulfide minerals, generating sulfur dioxide gas in a highly exothermic reaction. In practical terms, as fresh rock is exposed, the air flows in and the pyrite oxidizes to iron sulfate and sulfuric acid, releasing heat. Environmental engineers calculate that this reaction can push temperatures well above the ignition point of nearby organic material. Professor Jim Bowles measured that temperatures in the reacting shale reached on the order of 450 degrees Fahrenheit, about 232 degrees Celsius. That is hot enough to ignite combustible material and far hotter than a compost pile. What happens next is a classic chain of spontaneous ignition. The freshly heated rock immediately starts heating any bitumen or oil within its pores. That oil turns into flammable vapors, which ignite, producing visible flames and black smoke mixed with steam. A fire captain described exactly this. Even when the green plants were soaked, the rock itself continued to smoulder. In one video from April 2026, firefighters spotted a buried plastic drainage pipe actually on fire underground, apparently catching flame from hot gases escaping the rock. Crews put water on that pipe and the surrounding brush, and soon only the cliff fumes remained. Firefighters and geologists stress that this whole process is not caused by friction or an earthquake, but purely by the rock's chemistry. When smoke comes from the rocky cliffs, the immediate thought is volcano or even Solfatara. Both are incorrect. The smoking cliffs are not volcanic. The bluffs contain layers of iron sulfides and hydrocarbons, which, when exposed to oxygen from landslides or erosion, undergo a chemical reaction that generates heat and smoke. Although it was briefly called a natural solfatara, a term for a volcanic steam vent, experts clarified that this is not deep geothermal steam, just surface-level chemistry. In fact, this is similar to what happens in many coal or metal mines. Mine waste with pyrite often catches fire unexpectedly, sometimes for decades, because the sulfide keeps oxidizing deep inside. These fires produce smoke and can continue for years if left unmanaged. The Hope Ranch shale, rich in both pyrite and bitumen, behaves the same way. It is essentially a natural coal seam fire on a small scale. At the elevated temperatures produced, carbon materials can ignite and burn, producing carbon dioxide and carbon monoxide. All these chemical reactions produce recognizable byproducts. Burning pyrite emits a sulfur smell, and observers did report a strong sulfur odor. The white haze was largely water vapor and sulfur dioxide condensing. If measured, gases such as hydrogen sulfide and sulfur dioxide would likely be present. Scientists have even identified mineral evidence, tiny yellow crystals called hopper ankite or ammonium thiosulfate forming at the vent. This mineral forms when hot sulfur-rich gas cools and reacts at the surface, a clear sign of the chemical processes taking place. It is similar to minerals found near volcanic vents, but here the gases come from burning shale, not magma. Because this is well understood geology, fire crews know how to handle it. They treat it like any brush fire once flames reach vegetation. In 2026, crews poured water on the flames and controlled the spread. They stopped the forward progress of the burning pipe and brush. After that, it was mostly monitoring. By that afternoon, the scene was under control. No structures were threatened and no evacuations were ordered. The only risk was to plants and the hillside, not the town. Typically, these fires do not cause significant damage and are easily managed once contained. One interesting aspect is that the smoking spot tends to move over time. Each landslide or erosion event exposes a fresh patch of sulfide-rich rock. Over many years, the hot spot has shifted slightly east or west. Geologists observe the same pattern. After one event, the next smoking patch may appear a few dozen yards, or about 30 yards, which is roughly 27 meters, away the following season. There is no single vent. It is a shifting zone of smouldering shale along the bluff. Outsiders sometimes wonder how this could be mistaken for a volcano. The visual and chemical signs, smoke, heat and sulfur smell, are exactly what people associate with volcanic activity. However, there is no magmatic source. There are no active volcanoes in this region. This is spontaneous combustion, not volcanic eruption. There is no molten rock involved, the energy source is purely chemical. This event belongs to a broader category of natural burning ground phenomena. Along California's coast and elsewhere, similar events occur where natural gas seeps or sulfide-rich rocks ignite. Around the world, coal seams can burn underground for years, and gas vents can ignite when exposed to a flame source. The Hope Ranch event may seem unusual locally, but scientifically it is a known process. What turns this event from a strange coastal curiosity into something far more thought-provoking is what it quietly suggests beneath the surface. If gases are escaping, if heat is building, if rock is literally burning from within, then a deeper question begins to form. Could this be harnessed? Could the same process that creates smoke and flame along the bluffs be turned into something useful, something controlled, even something valuable? At first glance, the idea of capturing the escaping gas might seem reasonable. After all, the area around Santa Barbara has a long history tied to oil and natural gas. Offshore platforms, natural seeps, and petroleum-rich formations have been known here for over a century. The gas being released during these bluff events is indeed flammable, composed of light hydrocarbons and sulfur-bearing compounds. In theory, flammable gas can be captured, stored, and used as fuel. But the reality here is far less promising. The key limitation is scale and consistency. The gas released from these events is not flowing from a stable reservoir under pressure like a conventional gas field. Instead, it is generated in small, irregular bursts as rock undergoes oxidation and thermal breakdown. The flow is weak, unpredictable, and short-lived. One day there may be visible smoke and measurable gas output, and the next day it may drop to almost nothing. There is no steady pipeline of fuel to tap into. Attempting to capture it would require infrastructure that far outweighs the value of the gas itself. In energy terms, this is more like a slow chemical leak than a usable resource. Even deeper underground, while the Monterey Formation does contain significant hydrocarbons, most of the economically viable reserves have either already been explored or require advanced extraction methods such as hydraulic fracturing or offshore drilling. The shallow hydrocarbons exposed at the cliffs are remnants, fragmented and partially degraded. They are not concentrated enough to support commercial extraction, especially in a coastal residential area where environmental restrictions are strict. So while the presence of gas is real, its economic potential in this context is extremely limited. This leads to a broader concern. If gases like these can accumulate and ignite here, could similar hidden pockets exist beneath other coastal communities? The answer is yes, but with important conditions. Regions that share a similar geological makeup, meaning organic-rich sedimentary rocks, shallow hydrocarbon deposits, and the presence of sulfide minerals, could potentially experience comparable events. However, not every coastline has this combination. The unique tectonic setting of the transverse ranges plays a major role. The uplift and exposure of these rocks bring deep materials close to the surface, something that does not happen uniformly along all coasts. Even in places where the right ingredients exist, the trigger is crucial. Without erosion, landslides, or human disturbance exposing fresh rock, the reactions remain dormant. That means the risk is localized and conditional, not widespread or constantly active. Still, it is a reminder that beneath many landscapes, chemical processes are quietly unfolding, often unnoticed until they suddenly become visible. And that may be the most important takeaway from the Hope Ranch event. It reveals that the ground beneath our feet is not static. It is chemically active, storing energy in minerals and organic compounds that can be released under the right conditions. These processes operate on timescales that are invisible to daily life, but can manifest abruptly when geological conditions change. What appears to be a sudden event is often the result of millions of years of accumulation meeting a moment of exposure. Naturally, this raises concerns about safety. How dangerous are these gas seep fires to nearby homes and people? In most cases, including this one, the risk is relatively low, but not negligible. The fires themselves are usually small and localized, confined to the immediate area of exposed rock. They do not behave like wildfires driven by wind and vegetation, at least not initially. However, if flames spread to dry brush, the situation can escalate quickly, especially in fire-prone regions of California. The gases themselves also pose risks. Compounds like hydrogen sulfide and sulfur dioxide can be harmful if inhaled in sufficient concentrations. In open air, these gases typically disperse quickly, reducing the risk to nearby residents. But in confined or low-lying areas, there could be temporary build-up. This is why authorities treat even small events seriously, ensuring that air quality and fire spread are monitored closely. Could something like this happen again, without warning? The honest answer is yes, but with nuance. While the exact timing of an ignition event is difficult to predict, the conditions that lead to it are well understood. Erosion, cliff collapse, and exposure of fresh sulfide-rich rock are the primary triggers. These processes are ongoing along the coast, meaning the potential for future events is always present. However, they are not entirely random. Certain signs often precede them. One of the earliest signs is increased erosion or small landslides along the bluff face. Freshly exposed rock surfaces, especially those darker in color due to organic content, are more reactive. Another indicator can be subtle warming of the ground, though this is not easily detected without instruments. In some cases, faint odors of sulfur may appear before visible smoke, suggesting that low-level reactions have already begun beneath the surface. Visible smoke is, of course, the clearest sign that the process is active. At that point, the reaction has reached a stage where gases are escaping and heat is sufficient to sustain combustion. If the intensity of smoke increases rapidly, or if flames begin to spread beyond the rock into vegetation, the risk level rises significantly. Authorities rely on a combination of observation, experience, and standard wildfire response protocols to handle these events. Local fire departments in areas like Santa Barbara County are already familiar with this phenomenon. When reports come in, crews respond as they would to any brush fire, assessing the source, containing visible flames, and ensuring that nearby areas are not at risk. Monitoring does not typically involve continuous surveillance of every bluff, but rather targeted response when events occur. In some cases, thermal imaging tools may be used to detect hotspots beneath the surface. Gas detection equipment can also be deployed if there is concern about air quality. Once the immediate risk is controlled, the site is often left to cool naturally, as extinguishing the reaction deep within the rock can be extremely difficult. Long-term mitigation is limited because the underlying cause is geological. It is not practical to remove all sulfide minerals or hydrocarbons from the cliffs. Instead, management focuses on reducing secondary risks, such as clearing nearby vegetation to prevent fire spread and restricting access to active areas during events. What emerges from all of this is a clearer understanding of how subtle and powerful Earth processes can be at the same time. A seemingly harmless bluff overlooking the ocean can contain the ingredients for fire, gas release, and chemical transformation, all hidden until the right moment. The Hope Ranch event is not just a local curiosity. It is a window into the quiet complexity of near-surface geology, where chemistry, structure, and environment intersect in ways that can surprise even those who live right beside it. And perhaps the most striking realization is this: there is no need for deep magma chambers or dramatic tectonic upheaval to produce something that looks and feels like an eruption. Sometimes all it takes is ancient organic matter, a reactive mineral, and a breath of oxygen to turn solid rock into a fleeting display of heat and smoke. For residents, the key takeaway is that this is geology, not a developing disaster. When smoke appears, it should be reported, but it is handled like a small wildland fire. Fire crews monitor gases and allow the reaction to burn out once surface fuels are gone. By the end of the event, only scorched rock and faint steam trails remain. For those interested in science, this is a striking example of how buried hydrocarbons and minerals interact with oxygen. It shows how heat, gas and mineral formation can all result from natural chemical reactions. The discovery of minerals like hopperanchite at the site highlights how much can be learned from these events. In the end, the so-called Hope Ranch volcano is not a volcano at all. It is a natural chemical fire within the rock, driven by sedimentary shale, oil and sulfide minerals reacting with air. It is a recurring and well-understood process. There is no lava, no eruption, and no hidden magma chamber, just earth chemistry briefly revealing itself at the surface.